I got this temperature sensor, and it puts out the voltage that is proportional to temperature. Took it to the lab, hooked up a voltmeter, and then we made measurements, right? And so I nicely plotted temperature as a function, voltage, this voltage here as a function of temperature, and that's how it looked like, right? So I mean, I got many points here and made a line. It was really a nice straight line, so it's a very good temperature sensor. Okay. You will have to think. You will have to stop thinking about the quiz. You'll think about the quiz again a little bit later. I'll post it also on the web, so you can see that. And again, the discussion GSIs and in office hours, and I will explain it all to you. I just can't get your attention anymore. Huh? The quiz is overwhelming. Well, it's a good thing. So now you really think about this. What is that? Why is that voltage zero? Or how do I apply KVL? But please give me a little bit of attention. Otherwise, the next quiz is going to be really hard because, right? Because I tell you everything that you need to know in order to solve the quiz, but you need to listen. Okay, so I have this temperature sensor. I hooked it up to the voltmeter. That's what I got. So it's a good temperature sensor. But the problem was that the voltage was kind of small. I got a few millivolts of change over like 100 degrees of temperature change. So then I said, well, gee, that's no problem. We learned about amplifiers in EE40, so I applied one on the circuit, and I use this down here, right? I have the temperature sensor. I have this amplifier stage. Is inverting or non-inverting? It's inverting, right? It's an inverting amplifier. What's the gain? Is it 100? Minus 100. Okay, so the gain is minus 100 because it's an inverting amplifier. And then, so the output now, Vy should be 100 times larger or minus 100 times larger than what I just plotted before. So actually I would expect that the new thing would be extremely steep here, right? That's what I would expect, if at least the absolute value, right, would look like this. But that's not what happened. What happened was it actually was smaller, and on top of that it wasn't even linear anymore. It was sort of, first it went at some constant slope, but then it started even, the slope started to change. I was really upset, right? I mean, we do all of this stuff with operation amplifiers. We think that we understand them. Then I try to use it and it doesn't work. So, what's wrong? Did I just tell you a whole bunch of baloney? Yes. Okay, if the output resistance of the temperature sensor changes as a function of temperature, then you would see something like this. Right? Okay, we'll look at this into a little bit more detail. So at least one of you already understood the problem. That was actually the correct answer. So you can go and enjoy the sun, or you can listen to my version of the same explanation, but a little bit longer. Okay, so here is the analysis, right? What we really assumed here implicitly, and didn't say anything. We didn't say it, but we really assumed here was that this current here was zero, right? And here also the current flowing here was zero. That's what we really assume, because of course if there is current flowing also, then that current could produce a voltage drop, and that could precisely lead to the phenomenon that we just observed. So the next thing I did in the lab is I went and measured what current was flowing here, okay? And doing that, I actually found that I could model that big voltmeter just as a resistor. And that's what I show here. So that's really a model, a circuit model for the voltmeter that just captures the fact that there is actually a little bit of current flowing into the voltmeter when I make a measurement. Ideally, what would that current be? Zero, right? When we make a measurement, you don't want to disturb at all our circuit. You don't want that new current start flowing that didn't flow before. But of course, we know that maybe we can approximate that ideal solution, but not quite. It turns out voltmeters, they have internal impedances of typically 10 megohm, electronic ones. Okay? So based on that, right, if for example we had 1 volt there, we would have a current flowing that would be 0.1 microamp or 100 nanoamps. So it needs a little bit of current, not a whole lot, but it needs a little bit of current. What about now this amplifier here? Well, let's analyze this. What's the voltage at this node? What's the voltage at this node? Why do we know that? Well, because here we have a negative feedback loop, this minus sign here, and consequently the voltage at these 2 points are equal. Question 3 on the quiz. That's why you just could write down what the answer for question 3. Right? Okay, so if here we have a voltage Vt, and here we have a voltage 0, the voltage across the resistor R1, of course, is Vt, and therefore the current flowing through it is Vt over R1, that's It, and the ratio Vt over It then is just equal to R1. So here this actually is equal to R1, which happens to be 1 k ohm here. Okay? So really, what we are doing when we are hooking that operational amplifier up to a temperature sensor, what we are doing is we are connecting a 1 k ohm resistor to the temperature sensor. Now if this is a itty bitty little good temperature sensor but not very powerful to drive a lot of current, well then it may not like that 1 k ohm. It's sort of like you had a little oak, but then you put the big tog in front of it. If the tog doesn't move, you can row as much as you want, right? It doesn't move anywhere. Okay, so that's part of the thing. So I now replaced the DVM with that 10 megohm resistor, and I replaced the amplifier circuit with the 1 k ohm resistor, and now I want to figure out what's going on. So I also need to model my temperature sensor, and I can model it, of course, with a Thevenin equivalent, right? We've done that many times. Now I have the temperature sensor, which is some voltage source, and the voltage of the temperature sensor, of course, is proportional to temperature. That's why it's a temperature sensor. And then it has a resistance that we usually refer to as the output resistance. And I found that for my temperature sensor, this resistance was on the order of 120 kilo ohms. But as your colleague said, it actually varied a little bit as a function of temperature. And consequently, even this isn't quite correct, right? So it's sort of roughly 120 k ohm, but it changes a little bit. Okay, so now let's look at what that voltage Vx is. This voltage here, Vx. Okay, in the first case when we connected the digital voltmeter, so here we now close this connection, right? So that's what we really do. That's really the circuit that we have if we have that digital voltmeter there. Did you solve the quiz? No. Okay. So here, what is Vx as a function of the V10? Well, what is that circuit of the resistor, or S, and the resistor, or DVM? It's a voltage divider, right? And so the voltage out, of course, is just given by the ratio of that voltage divider, so that would be R dVm over R dVm plus Rs. Now, because Rs is much smaller than R dVm, we can now actually more or less ignore this, and then this is very close to 1, right? So if we hook up that voltmeter, then indeed we measure actually V10, okay? And that's what we want. And the reason we do that is because this RDVM is very large. It's much larger than RS, okay? Now in the second situation, at the bottom of the slide, we again have such a voltage divider. So we have ROP, that was R1 in the slide before, RS plus ROP. It turns out that ROP is negligible compared to RS. So this is on the order of 1 over 120, right, approximately. Right? And it varies a little bit because RS varies a little bit. That's exactly what your colleague said. Okay? Right? Makes sense? So what apparently happened when I connected the amplifier circuit is that first my signal was divided down by a factor of a little bit over 100. And then afterwards, the operation amplifier kicked in and put back that factor of 100. But overall, of course, 100 over 120 is still a little bit less than 1. So overall, I actually put an attenuator. And that's exactly what I've seen here. The blue curve, right? That is 100 divided by 120. Okay? That's a little bit less than 1. Therefore, a little bit less than between 1. Okay? So even though we put an amplifier there that has a gain of 100, we ended up with less signal out than before. And of course, that's not very desirable here. Actually, it's very bad in this particular case. So what could we do about this? Yes?
Use a non-inverting op-amp or some other that draws.
Okay. Okay, so we need to somehow make sure that we don't pull that much current out of our temperature sensor, because our temperature sensor is really a temperature sensor. It's not meant as a voltage source that can put a lot of drive, right? It cannot put out a lot of current. Okay, so here is sort of a summary of what happened, right? In general, and that would be the same if we had not a temperature sensor but the pressure sensor, or God knows what. We can model this, we call it here the source. We can model this with the Thevenin equivalent, and then we get the resistance RS. That of course depends on the sensor. For a temperature sensor it was about 120 kilo, but for some other sensor it's some other number, right? And sometimes it's much smaller, and sometimes it's even much bigger. And then we have a load here, and again that could be our operation amplifier. The load was 1 k ohm for the resistors that we had chosen, and in some other cases we use a DVM or whatnot, and then the resistance can be much larger. So in general then, of course, if we want to, what we really measure is the voltage VL. What we actually want to measure is the voltage VS, right? We are not really interested in VL, that just happens to be a function of all these resistors. That can be whatever they want to be, but what we are interested in is what is VS, right? That's really the question that we are trying to answer. And so we can figure out the ratio VL, which is what we measure, to VS, which is what we actually want, and that ratio should be equal to 1, right? Or at least a constant, right? Ideally 1. Okay, and so, of course, we have here again that famous voltage divider, and already put the equation here. And we can see, for finite values of RL and RS, this ratio is always going to be less than unity, unless we would have negative resistance, but let's forget about those for the moment, okay? So this ratio is always going to be less than 1, but of course we can make it that it's very close to 1 at least, right? And there are two situations how we can make it very close to 1, and you can see that either mathematically or you can see it just from circuit intuition, and they are also written here on the paper. So the first one is if we make RL very, very large, ideally infinite, but at least much, much larger than RS. If RL is 100 times RS, well then we sort of get a 1% error. If it's 1,000 times RS, we get a 0.1% error. If it's 1,000,000 times larger, then we get a 1 ppm error, and so on, right? So we can make that error so small that ultimately in our application probably doesn't matter anymore, right? So that's the first situation. If you make RL really, really large, well, then that ratio is going to be essentially 1, or as close to 1 as we possibly would want or need in our application. Okay, and of the two cases that I showed you, which one implements this? Well, when we had the voltmeter, right? The voltmeter really had an RL that was 10 megohm, that was almost 100 times larger than the 120 k ohm, and so the error was really small, right? Okay, sort of a percent, and that I couldn't see on my graph, right? So that's the first condition. The other condition is also kind of obvious if you look at this. Of course, if you would make RS equal to 0, if you had an ideal voltage source, well, it wouldn't matter how much current you pull, how much current goes through RL, and therefore the value of RL wouldn't matter. VL would be simply equal to VS. So either of these two situations allow us to make that ratio 1, and then we measure VS and not VL. Okay? Or they are the same. All right, so I also give you, so how somehow try to understand it. I give here a sort of a loose analogy, right? Imagine that you have a car engine, right? And you want to drive you want to use it in your car. So obviously, one thing, if you want to be able to go up to 120 miles or better kilometers. So whatever, if you want to go up to a certain speed, well, you need a certain RPM, right? Of the engine, right? You need an engine that is capable to at least turn at a certain RPM, right? But is that enough? Well, no, of course not, right? You cannot take a small little electric motor that will put out really a lot of RPM connected to your car. It's not going to move, right? What you really need also is you need to have a certain amount of torque or output resistance so that this engine is actually not only capable to go fast enough, but it also is capable to supply enough power or torque to the wheels that actually spin around. That's exactly the same thing here. We need an RS that isn't too large, otherwise you can't drive this RL. Okay. And so operation amplifiers actually can do that. Well, it sort of looked like in my example they can't, but actually they do. And so let's look at that, how we realize this. Now, so this is the situation that we just analyzed before, and actually we already said that, well, because the voltage at the input of the operation amplifier is 0, the difference of those two voltages, really the input resistance, the current is just determined by R1, and the input resistance in this case just happens to be R1. So this ratio here is just R1, we just calculated before. Well, what is this test current? Whenever I want to measure the input resistance, what I really do physically in the lab is I connect the source, maybe the lab power source, to the input of my circuit. I call that VT, the test source, okay? And then I measure the current, right? And the ratio, that's the resistance, at least for that voltage, okay? So, so in this case, what is IP? Yeah, exactly. That one's 0, and consequently, this one is on the other limit. It's very, very large. Okay. So there is apparently between inverting and non-inverting amplifier, there is some very significant difference. In the inverting amplifier, we actually have current flowing into the thing, right? And the input resistance happens to be R1. In the case of the non-inverting amplifier, well, then we have almost no current flowing into it, ideally no current at all. And then the input resistance is infinite, and we can use that in our circuit with the temperature sensor. Now I show again the temperature sensor, but this time I show its Thevenin equivalent, and then instead of directly connecting it to the gain amplifier, I connect first the buffer, a non-inverting amplifier here. What is the gain of this stage here?
0.
Oh, no, better not 0, huh? Yeah. Okay, the gain of this is just 1. Actually, we can see that very easily. How can we see that? Well, it's negative feedback. We see that right away. The voltages at the two input terminals of the operation amplifier are the same. Well, one of the two input terminals actually connected to the input. The other one's connected to the output, so the input and the output must be the same. That's what this circuit does. No equation, right? Obviously, if here you have the input, Vi, and here we have the output, Vout, and they are identical, well then Vout is equal to Vi, right? We didn't need to write an equation for that. And the reason that's true is, well, we have negative feedback. Okay, and then afterwards we go into the next stage here. Okay, so in this case now the gain is going to be 1 of that non-inverting amplifier times the gain of this one minus 100, and it's going to be minus 100. Okay, and it's totally independent of RS. You can go change RS as much as you want, as long as you don't make it really, really, really large, make an open circuit or something or smooth like that. Then it really just doesn't matter what RS is. Yes. Because let's call this Vi. Right. So what this is equal, it's V out over V temp is equal to V out over V out prime, with this being V out prime, right? Times V out prime over Vi times Vi over V temp. Okay, and then we have this one here being minus 100. The next one here, this guy here, V out prime over Vi. We just said that that was 1, and then finally this one here we had, well, because there is no current flowing through RS, the two voltages are identical. There is no voltage drop across RS, so then this one is also 1. And now you see that, hey, we got to multiply them together, right? I just simply broke this equation up into lots of parts. Incidentally, that is a very good, we don't need that too much in EE40, because usually in EE40 things are relatively simple and you don't have very long chains of things. But in general, that's a very good thing. If you have any kind of a problem, right, you have lots of pieces to the problem, one after the other, so then you can do a decomposition. As I just showed you at the top, instead of trying to find out what is V out over V temp, which may be a very complicated thing, right? In fact, how are we going to figure that out? It's going to be 20 equations with at least as many unknowns, and so how are we going to solve this? You can break it up using this multiplication trick here that I showed you. And obviously this is an identity, right? You know that from whatever your first course in algebra. And then every piece in that long product is perhaps much easier to figure out what it actually is than the overall thing. And then you just multiply together. Okay? So good question. All right. So this is how we actually deal with, for example, that. Let's see. So applications of this. Right? Now, why is this important? Well, I mean, here is an application that we, of course, already saw that when we want to measure the voltage somewhere in our circuit, then really what we want to do is we want to figure out what is the voltage, but we don't want the current to flow there. And that's why the internal resistance of these voltmeters is very high. And there is, of course, an operation amplifier inside. Go and rip it apart. No, that's not the one in the lab. Go buy your own and rip it apart. You'll find the operation amplifier, and that's what is in there that makes it that current is almost zero. Now, obviously, if you want it, it's 10 megohm the internal resistance. If you have a sensor that has much higher internal resistance, like a pH sensor electrode, then that may not be enough, and then you get an error, even with such a voltmeter. Incidentally, also these digital voltmeters. That's sort of the advantage of them, that their internal resistance is very, very large. The old analog ones, you actually have to supply enough current for the meter, for that tank to actually move, and so they have much lower internal resistance, a few 10 kilo. Okay, but this one has a. So now we always use these digital ones. Actually, the analog ones you hardly can buy anymore; they're very expensive. But the digital ones, they have very high internal resistance. Okay, so another application here. Well, this is kind of a tricky application, trickier than the quiz. But it's very interesting what's going on here. So the first thing that in order to solve this problem is, again, we want to apply a little bit of insight before we hit it with equations. So what's the voltage? What's the voltage between these two terminals? Well, it's Vi, right? I wrote it there. It really doesn't matter how much current II is flowing there. It's always going to, the voltage there is always going to be Vi, because that's what I said it, right? I could just call it Vi. Okay? So therefore, it really doesn't matter how much current flows into RF, and therefore the value of RF really doesn't matter if I want to figure out what the voltage V out is here. Okay? Likewise, the operation amplifier's output, it can provide really a lot of current. It's like a voltage source at its output. Right? It provides the operation amplifier is like a voltage source. It defines what voltage there is at the output, it's actually the V plus minus V minus times the gain, right? That's the voltage there. It doesn't matter how much current it has to supply. So in particular, it does not matter how much current flows into RF. So it really doesn't matter what the value of RF is. And RF equals infinite would be just as good as any other value. Okay? The circuit, the voltage V out is going to be the same regardless of whether RF is 1 k ohm, 100 k ohm, mega ohm, or infinite. Well, why is infinite such an interesting thing? Well, how could I redraw my circuit if RF actually was infinite? Yeah, exactly. I could remove it. Now it's not so easy to remove. Well, no, I'm not going to do that. It's a waste of time. But anyways, think of. Well, actually, think of it not being here. Right? It really doesn't matter. Right? Okay? It really doesn't matter. The voltage V out is going to be exactly the same whether the resistor's there or not. Okay? So why is this useful? Well, because now the circuit is much easier to analyze. If you didn't know that, or if you didn't figure that out, you could still solve the circuit using node voltage analysis, or God knows whatever technique we learned in class. That's perfectly fine. It's going to take you 5 minutes instead of half a minute, and therefore you may run out of time on the quiz. Or you may run out of time of it's difficult to understand circuits, right, if you just apply equations. Yes?
Why is V0 independent of RF?
Why is it independent? Well, because as we argued, these two currents, these two green arrows here, it really doesn't matter what current flows there. Right? The voltage VI is totally independent of the value of II, because I set it VI and I called that VI, right? The amplifier at the output is like a voltage source. It dictates what voltage is there, and if it's an ideal operation amplifier, if it has to supply 1,000,000 amps for that, well, the operation amplifier is ideal, it will supply that 1,000,000 amps. It will simply hit the voltage. The voltage at the output of an operation amplifier is simply the difference of the input voltages times the gain, which for an ideal op amp is infinite, which is the reason why at the input actually the voltage difference 0 for an ideal operation amplifier with negative feedback. In practice, of course, a real op amp is not going to supply 1,000,000 amp, but then mostly we wouldn't want to, right? I mean, we make RF a few k ohm, and well, then the current that's going to flow is a few milliamps, right? And so even practical op amps, most of them, they happily supply a few milliamps, all right? So it really doesn't matter what the value of RF is. And so now if I want to analyze my circuit, figure out what is V out, I can just analyze it for the case where RF is infinite and then RF isn't present, and that's why I erased it. Yes?
So you said VI is independent of II, right? So like they're not dependent on each other. But like if you write a KVL for the whole amplifier, so you ask V naught, and then you go through RF, and then you came back to VI, then that means that your V out is dependent on RF. Does that make sense?
Well, the value of V out is going to change if I change VI. No question about that. So that connection is there. But we're going to be careful about the causality. I put the certain VI there, then I get the certain V out. It's not that I get the certain V out and then somehow miraculously VI happens to be some value, right? I connect my... what I'm really saying is that what I actually do here, when I do the test, I connect. I simply connect a voltage source here, right? That's what I'm really doing. Then, of course, the voltage there is VI, totally regardless of how much current. Yes?
Because after it says negative positive feedback.
Oh, that's a good thing. Actually, there is no feedback there. Why is there no feedback? Well, the voltage here is unaffected by the value of RF, right? even though current flows and so on, the voltage here is set by this source. It's not set by the current flowing through RF. That's why, even though it looks almost like there was a feedback loop, there isn't actually a feedback loop. I do not affect the voltage at this terminal by the output voltage of my op-amp. Consequently, there is no feedback. Right? No? If I change the voltage here, if for some reason the voltage there changes from 0 volt to 1 volt or 1 volt to 10 volts or what, no. What is the voltage, how is the voltage here going to change? Well, let's say VI has a certain value, let's say 1 volt. And then Vout, I change it from 1 volt, let's say, to 2 volt. It somehow, for some reason, it changes from 1 volt to 2 volt. God knows why. Okay? What is the new value of Vout now? Of VI now, excuse me. And it's still 1 volt because, hey, it's a voltage source that just says the voltage there is 1 volt. Right? It's totally independent. The value of Vout can change as much as it wants. This voltage source, hey, I'm a voltage source, I put out 1 volt. I don't care what the voltage somewhere else is. I'm a voltage source, I put out 1 volt. Yes?
That right there does require that RF be non-zero value because
Yeah. Okay, fine. Yes. If you're a mathematician, then you can say every one of these components can actually have 0 value and so on, and then it's a short circuit. And if you have a short circuit, if you actually would make RF equals to 0, then you get into mathematically or at least practical, totally idiotic situation because you have this guy telling what the voltage is there, and then you have also the operation amplifier telling what the voltage is there, and if they're not equal, how they're going to fight it out. They're both infinitely powerful. It just makes no sense whatsoever, right? So yes, you're absolutely right. Technically, if I was a mathematician, I decorate all my slides with RF not be 0 and not negative, or all sorts of stuff like that. You can't build it in a lab anyway, so why should I even worry about it? Okay, so it was a correct comment, but we don't need to worry about it. So I'm still not sure. Have I answered your question? And the one behind?
I mean, like, I understand that, like for amplifiers, the R is always equal to A, or A is B multiplied by A.
Mm-hmm.
I understand that.
Yeah.
Or, so you're saying that the R is only dependent on the I. Well, like, when you write a KVL for the whole circuit, it's just like, it's dependent.
Okay, fine. So let's just do that. Let's analyze the circuit now. Let's not do this with KVL, but let's analyze the circuit as we have it now and figure out what is this V out here, V out over VI. What is that? Well, we have now that we sort of argue that the RF doesn't matter what the value of RF is, we can recognize the remaining circuit as what is this? No, it's not just the voltage divider, right? There is an operation amplifier there. Somebody said it. This is a non-inverting amplifier, right? So. This is a non-inverting amplifier. The gain of this thing is what? It's actually the ratio of these two resistors here plus 1, it's 10. And if you don't remember that, well, look at your homework, look at your book and so on. Or even if you still are not sure whether you can ignore RF or not, go and use node voltage analysis or something like that and solve the problem for 3 different values of RF. Maybe then it clicks or so. Okay? So this ratio is actually 10x. So now let's go back to actually making this resistor appear again. Okay, so now let's figure out what is the so V out is equal to 10 times VI, right? And it doesn't. yes, they're connected together, but if we solve this correctly, and I promise I didn't make a mistake, then this doesn't depend on Rf, because 10 is a number that does not depend on Rf, right? Of course. Okay, so then what is the current II? Well, that's the current here. Well, what is that current? Well, that is equal to Vi minus V out over Rf, right? And that is equal to Vi times 1 minus V out over Vi. Well, that happens to be 10 over Rf. So II over Vi is equal to minus 9 over Rf. Or if I turn this around, that means I'm running out of space here, but if I have Vi over II is equal to Rf over minus 9. So Rf is a normal resistor that pulled out of the drawer, and it maybe has a value of 9 kilo ohm. What is that Vi over II? 1. Minus 1 kilo ohm, right? Minus 1 kilo ohm. Minus! Hey, this guy is minus 1 k ohm. Okay? So this whole circuit looks to this source here, to this Vi. This whole business looks like all of this stuff. It acts just like a resistor Rx, and the value of this Rx is minus 1 k ohm. Okay? So yes, you cannot go to Radio Shack and tell them, hey, you know, I want the negative resistor. But you can go to Radio Shack and tell them, I want a couple of resistors, a 3, and I want an operation amplifier, and then you can build this circuit, and you actually build a circuit that implements a negative resistor. If you stick also a battery inside and put it in a nice black case that nobody can look through, give it to somebody, and he measures and doesn't so on, and says, well, what you have here is bloody miracle, it's a negative resistor. Okay? So that problem, homework 2 or 3, or I've forgotten, that problem was a little bit sheepish, but totally plausible, totally possible. I could have just as well sent you to the lab and given you that problem to solve it, and the instruments and everything would have told you, well, there is a negative resistor there. Okay? We can build this. Alright, I'll see you Friday again.